In part 2 of functions and graphs, we're going to be focusing on transformations of graphs. Okay, and this really shows you how beneficial vertex form is. So first we're going to use vertex form to find transformations. We'll focus on vertical and horizontal shifts. Okay, we'll see what that looks like in function form as well. And then we'll look at the a value, that leading coefficient, to see what it does. Okay? All right. So your goals for this lesson is to determine the vertical and horizontal shifts of a graph by looking at the vertex, right? And then to determine the vertical stretch, compression, and reflection of a graph by looking at the a value. And we'll talk about what all that means. So before we can talk about transformations, you need to understand what a parent function is. Right? A parent function is always what we refer back to when we're talking about how a graph is moving. Right? If I say it moves 2 units to the right, what does that mean? The right from where? Well, the right from the parent function. Okay, your parent function is the most basic form of a function family. So I've listed some of the most common ones you'll see this year here. Right? So these are 6 function families. You have linear, quadratic, exponential, cubic, absolute value, and radical. Okay, and these are the basic forms and what we call the parent function of each family. So for linear, it's just y equals x. Quadratic, which is what we're going to focus on most of the time, y equals x squared. And then you have your exponential, where your x is the exponent. Your cubic is x to the third. Absolute value with your absolute value bars. And a radical is talking about a square root or a higher root. Okay? So we're going to focus mostly on this one right now. Okay? So you need to know what the parent function graph looks like. And that's right here. This is the quadratic parent function. Okay? It's just y equals x squared. The vertex is at the point 0, 0, the origin. Okay? And that's important. That's what we're going to compare everything to. Because if you think about it, if I could take that vertex and take that point and move it around, you could see the rest of the graph will actually follow it, right? I could use that kind of as an anchor point and shift it up, down, left, or right, okay? And then when we talk about getting wider or skinnier, we're comparing it to this level of opening, right? So at the very beginning, it has a up 1 over 1 type of slope, even though we know the slope changes as it goes on, okay? Another way you could write the parent function rather than y equals x squared, which we call standard form, is we could actually put it into vertex form here, and you could see our a is 1. And then our vertex would be 0, 0. You don't have to have all those extra numbers in there, but that can kind of see how it relates to vertex form. Okay? So we can use vertex form to find the transformations, because if I know how the vertex moved, then I know how the graph moved. Right? And if I know the vertex is starting at 0, 0, then it'll be very easy to tell if it has different numbers which direction it moved. So the first thing you want to do is find the vertex. Okay, if you can find the vertex, you can find where the graph moved. And then you're going to compare your vertex to the origin, right, which is the parent function. If it has a positive x value, that means you're going to the right, right? Positive x values are to the right. Negative x values are to the left. If your vertex has a positive y value, then it went up. If it has a negative y value, then it went down. Okay? So let's give it a try here. So example 1, I have f of x equals x plus 3 squared minus 4. So first thing we want to do is find our vertex. So in this case, our vertex is negative 3, negative 4. Right? It's the opposite here, the same here. So then just think about, where is negative 3, 4 on the graph? Well, you can just do a quick sketch. I know my parent function is starting here at 0, 0. And now my vertex is moving to negative 3, negative 4. Well, I know negative 3 is here to the left. Negative 4 is down here. So it went boom, boom. Right? So, and then it went like that. Right? So my vertex moved left 3, down 4. And that's how I would answer that question. So to be more official, I would say translate left 3, down 4. So when we shift left or right, okay, that's called a translation. So left and down. And here is the graph that we can check that with. Okay, so you can see it kind of matches my sketch. We started here at 0, 0, went left 3, down 4. Okay? So let's see if you can try, sorry about that, find the vertex and tell me how it translated. Okay? So in this case, the vertex, oh goodness, there we go. Our vertex was 2, 3. Remember, opposite sign, same sign. And if I think about that on a coordinate grid, then positive 2 would be over here, positive 3 would be up here. So our vertex moved from the origin, and it went right 2 and up 3. So we could say that it translates right 2 and up 3. So you see how the vertex can tell us if it's moving up, down, left, or right at all. Okay? And there it is. We went from the origin, right 2, up 3. And there is our new graph. Okay? Okay, so we can also look in something called function form. So this is what we call function form. Now, we don't know what the parent function is. It just says the function f of x. But if we pay attention to where our number is being added or subtracted, then we can relate it in the same way. Notice that our h was inside with our x, right? And it was the opposite of what we saw here. Our k was outside of the parentheses, after the x, right? Outside the parentheses, right? And the sign matched. So we can actually translate that knowledge to generic functions. So notice here our number is after the parentheses. So that means it's like a k value. So our k values were our y value. It was moving us up and down. So if our k value is -6, then that means that we went down 6 from the function f of x. Whatever this new function is, it's 6 lower than what f of x is. Okay, we're subtracting 6 from the function, and that's moving your y value. F of x is your y value. So it's doing the same thing as your -4 did up here. It moved you down 4. Okay? So we can continue to translate over here. F of x minus 5, then plus 7. So notice our -5 is inside the parentheses, just like our h was up here. So we can think of that the same way we think of h. And it's the opposite. That translates as well. So if this were to have a vertex, we could say that vertex was positive 5, 7. If this one over here was to have a vertex, we could say that vertex was 0, -6. So if you want to think in that way, if that helps you find the transformations, you can do that. Now, we don't know if this was a quadratic, so that may not be an accurate vertex, but it does the same thing to the graph. Okay? So over here, how did this did this new function move compared to f of x? What are the transformations? Very good. It went right 5 and up 7. Okay? All right, let's look at another type of transformation. The leading coefficients, the a value. What does it do? All right? Well, I have 3 graphs to compare here. We have our parent function where our a is 1. We have this blue function here where our a is 3. And we have this purple function where our a is 1/4. Okay? So when the a is greater than 1, what's happening is our parabola is getting steeper. Think about a slope being bigger than 1, right? If you went up 3 over 1, up 3, that would be a really steep slope, right? So what's happening with our parabola is it's getting steep, right? So it was here, but it's getting steep on both sides. So it's squeezing it together, okay? And we actually call that a vertical stretch. Think about if it's pulling it this way. Vertical stretch, okay? Now, the reverse is happening when you have a fraction less than 1. Okay, we're still bigger than 0, but we're less than 1. Right? So if I had a slope of a line of 1/4, that would be up 1 over 4. Right? So it's going from a 1 over 1 slope to a 1/4 slope. Is really gradual. And the same thing's happening with our parabola. We're starting with a 1 style slope, and it's getting more gradual on both sides, so it widens it out, and we call that a vertical compression, kind of like somebody squishing it down, and I'll write those down in a minute, okay? So we could have those two things happen, get steeper or more wide. And then if A is negative, so here your A is 1, and here your A is negative 1, right? So what's happening is your Y values that were positive are becoming negative. And it would happen the other way too. If your Y values started negative, they would turn positive. So when you have a negative for your A, it's actually a reflection across the x-axis. So see how we're flipping on top to on bottom? That goes over the x-axis. So we can get a vertical stretch or compression, which is talking about how wide or steep. And A can also tell us if we have a reflection. Okay? And this is where I wrote it out all officially. When you're looking in vertex form, your A is in front. Okay? If A is positive, there's no reflection. We call that concave up. Right? So it looks like this. I like to say if A is positive, then it's like a smiley face. Right? So it's going up, concave up. If A is negative, then it's like a frowny face. Concave down. Okay? Which we call a reflection across the x-axis. And then here, I put absolute values around A because the negative and the positive does one thing, and then the actual value of the number does the other thing. So if the absolute value, so just the positive version of A, if it's bigger than 1, it's more narrow. It's a vertical stretch, stretching it up, right? If A is less than 1, right, the positive of A is less than 1, then it's a vertical compression. It's getting pushed down. It's wider. So let's practice listing all the transformations for these examples. So I'm going to see here that our A value is -2. Our H value, our vertex, let's do that. Our vertex is 0, -4. So what does A tell me? Well, A is negative. Negative tells me I have a reflection. So that's a reflection across the x-axis. Okay, now look at the positive of A. The positive A is 2. 2 is bigger than 1, so that's a vertical stretch. It's getting more narrow. And then our vertex, like before, nothing's happening left or right, but it's moving down 4. So that's a translate down 4. And that's it. Those are all your transformations. All right, see if you can pick out all the transformations for example 2. All right, we've got A of 3/4 and a vertex of -1, -2. Hopefully you caught that negative there. So that's going to be 3/4. It's positive, so no reflection. The positive of A is less than 1, so that's a vertical compression. All right, the vertex is -1, -2, so that would be translate left 1 and down 2. And there we go. Okay, I just wanted to show you here that you can see these in function form as well. So we don't know what the parent function is, but we can see all of the numbers and how they are going to affect the graph. Okay? So our A here was 3. Our vertex, if we were to have one, would be -7, 0. And we could tell what type of transformations are happening, right? So A is greater than 1, so that would be a vertical stretch. It's positive, so no reflection. So that means no transformation in that area. And then we are moving left 7, down 0, so that would just be a left 7. Okay, so can you name all the transformations for example 4? All right, and the answer to that would be a reflection. Okay, it would be a vertical compression. And we get that from that negative 1/2. The negative is the reflection. 1/2 is less than 1, so there's our vertical compression. There's no movement left or right, but there is movement down 14. And there's a quick overview of all your transformations.